We're diving into one of those classic physics puzzles that at first glance just looks like a total mess. You've got things moving up, things moving down, and we're supposed to track it all. But what if the trick isn't to follow the chaos, but to find a single hidden point that tells the whole story? Let's get into it.
I mean, this is the fundamental challenge, right? You're on a moving train, on a spinning planet, flying through space. Everything has its own frame of reference. The problem we're about to solve is a perfect, bite-sized version of that exact headache.
And if you're a physics student, you know the name Irodov. It means you're in for a challenge, but usually a really clever one. We're tackling problem 1.160. The setup is simple enough. A man, a ladder, and a counterweight, all connected over a pulley.
So let's really picture what's happening. A man starts climbing up a ladder, but as he climbs, his weight pulls the ladder itself down over the pulley, and on the other side of that pulley, a counterweight is moving up. So we have three different things moving in different directions. Our job? To find the one single shift in the system's overall balance point. Yeah, it sounds pretty complicated.
Okay, but here is where we're going to get smart about this. Instead of driving ourselves crazy trying to track every single piece, we're going to do something different. We're going to shift our perspective and look at this whole mess, the man, the ladder, the counterweight, as if it's one single object, one system.
And the tool that lets us do this, our secret weapon, is the center of inertia, which you probably know as the center of mass. Just think of it like this. It's the one single point where you could imagine all the mass of the entire system is concentrated. It's the balance point for the whole shebang.
And here's the really beautiful part. By focusing only on this one point, we get to ignore almost all of the messy stuff. All the forces, the tensions in the rope, the accelerations, we don't need any of it. We can solve this just by looking at where things started and where they ended up. It's an incredibly powerful shortcut.
So, to find where the center of mass ends up, we first have to figure out how all the individual movements are related to each other. We're not talking forces yet, just pure motion. This is what we call a kinematic approach.
The first connection is pretty straightforward. The ladder and the counterweight are hooked together by a rope that doesn't stretch. That gives us a really simple constraint. If that ladder moves down by, let's say, a distance d, the counterweight has to move up by that exact same distance d. It's a perfect one-for-one trade.
Okay, that was the easy part. The real tricky piece of the puzzle is the man. Now here's a super common pitfall. It's tempting to say his movement is just how far he climbed up the ladder. But you gotta remember, the ladder itself is moving under his feet. So here's the key insight for his motion. His total displacement relative to the ground is actually two things added together. He moves up the ladder by a distance the problem calls L prime, but at the exact same time, the ladder is moving down by that unknown distance d. So his actual change in height is his climb up minus the ladder's drop down. It's L prime minus d.
We are so close. We've related all the movements to this one unknown distance, d. But how do we find d? Or do we even need to? Well, it turns out the problem gives us one last clue, and it's hidden in plain sight in a single word.
Let's look at the problem statement one more time. See that? It doesn't just say there's a weight on the other end. It specifically says the counterweight of mass m. That word, counterweight, is not an accident. It means something very specific.
In physics, when you see the word counterweight, it's a signal. It's telling you that its purpose is to provide balance. The huge implication here is that before the man ever started climbing, the whole system was just sitting there, perfectly balanced. The forces on both sides of the pulley were equal.
And that gives us the last piece of the puzzle. If the system is balanced, it means the total mass on the left side, that's the mass of the man, m, plus the mass of the ladder has to be equal to the mass on the right side, which is the counterweight, m. And boom, just like that, we have the simple equation that's going to crack this whole thing wide open.
All right, the hard part's over. We did all the conceptual thinking. We have our secret weapon, the center of inertia formula. We figured out how all the moving pieces relate to each other, and we found that hidden clue about the masses. Now it's just time to put it all together.
Okay, let's line up our pieces. For the man's displacement, we have L prime minus d. For the ladder, it's just negative d. For the counterweight, it's positive d. Now for the masses. Thanks to our balancing clue, we know the ladder's mass is just the counterweight's mass m minus the man's mass m. And that means the total mass of the whole system is just the left side plus the right side, which comes out to exactly 2 times the counterweight's mass, 2m. Perfect. We have everything we need to plug into that main formula.
And now, for my favorite part, a little bit of algebraic magic. First, we substitute all those expressions we just found into the top part of our formula. Step 2, we expand it all out. It looks a little messy, right? We've got all these terms, and a bunch of them have that unknown distance d in them. But now, watch what happens in step 3. When you gather up all those terms that are multiplied by d, they perfectly cancel each other out. They just vanish.
And that right there, that is the big aha moment of this problem. That annoying unknown distance d, the one we never actually figured out, is completely gone from our equation. It turns out we never needed to know how far the ladder moved in the first place. The way we set up the problem made it totally irrelevant to the answer we were looking for.
So after all the dust settles from the algebra, we're left with this beautiful, simple result. The total displacement of the whole system's center of inertia is just the mass of the man, m, times the distance he climbed relative to the ladder, L prime, all divided by 2 times the mass of the counterweight, 2m. That's it. So elegant. So we got the answer, which is great. But what's the real lesson here? Why do physics teachers love giving out this problem? What does it actually teach us? Well, the biggest takeaway is all about strategy. We were looking at what seemed like a complicated dynamics problem, with forces and motion. But by changing our point of view, by deciding to track the center of inertia, we turned it into a much simpler kinematics problem. We solved it just by looking at the geometry of the motion, and we didn't have to worry about what caused it.
So I want you to think of this as a new superpower you can use. First, always think carefully about how you define your system. Look at the big picture. Second, hunt for constraints, things like that non-stretchy rope that link all the parts together. And third, and this is a big one, never forget to leverage the simple definitions. Sometimes the most powerful equation you have is the definition of something, like the center of inertia.
And that kind of leaves us with a final question to chew on. This technique, this way of finding a smarter perspective, isn't just for physics problems. It's a way of thinking. And it really makes you wonder, right? What other complex, messy, seemingly impossible problems out there are just waiting for us to find the right balance point to focus on?